Part 4 of the Introduction to Amateur Astronomy lecture series is entitled Telescope Tutorial. Before we dive into today's lecture, since we are well into the series now, allow me to give you a bit of a summary of what we covered thus far. So, another name for the Introduction to Amateur Astronomy lecture series is Richard Bell's four-step program to become a star-hopping sky master. So if you follow these steps, I guarantee you'll have a much smoother growth period to becoming an amateur astronomer. So as we mentioned way back in part 2, your first step is to not buy a telescope. It is the worst thing you can do, especially if you're uneducated about amateur astronomy in general, or specifically telescopes. Because I guarantee you'll buy the wrong one, you'll be very unhappy with it, and it'll end up in that weight room you never use, or most likely the closet, and you'll sell it for pennies on the dollar or give it away to Goodwill or Salvation Army or something like that. So the very first thing you should do is to educate yourself. That's what I spent most of my youth doing, well into my teens and probably early 20s when I finally got my first serious telescope. So I read a lot and watched a lot of documentaries. For me, back in my day, it was Peterson's Field Guide to the Stars and Planets. That's the book that taught me all the basics of astronomy. But today, there are lots of books specifically geared toward amateur astronomy. So the ones we mentioned in part 2 that I really recommend are the Backyard Astronomer's Guide or Night Watch. They are both excellent. The Practical Astronomer is also very good, and that's more for those on a strict budget. It's a bit less expensive than the other two. So if you can't really afford Night Watch or the Backyard Astronomer's Guide, hopefully the Practical Astronomer is within your budget. And yes, there is plenty of information online, but as I mentioned back in part 2, the best information is still in books. Then step 2 is to learn the night sky. So, for example, if you do not know how to find the Big Dipper in the sky, you should be able to do that without a star map alone. So I think pretty much everyone can handle that unless you're in the southern hemisphere. But if you don't know that these two stars point directly to Polaris, the North Star, then you're not ready for a telescope yet. So you got to know how to use the pointer stars to find Polaris. I mean, is it 100% required? No. Does it help you find the stars and stuff on your own? Yes. I mean, everyone uses the special apps and go-to computer functions and smart telescopes today, but still, if you're really eager to become a seasoned amateur astronomer, you have to know the night sky. And of course, part 3, we covered binoculars, and that is also step 3. So binoculars, again, fill the gap between what the unaided eyes can do and what a telescope can do. Your eyes have a very wide field of view. Telescope has a very narrow field of view. Binoculars fill that gap. And you can use the star hopping techniques that you use to learn to find deep sky objects with binoculars with a telescope, assuming you're using a non-go-to telescope. And then finally, where we are today, step 4 is selecting a telescope. Now, again, before we talk about telescopes themselves, we have to talk about the terminology behind them. And it also helps you learn the basic attributes, so the most important attributes of any telescope. And by far, the most important feature of a telescope is its aperture. So the aperture is what most people refer to when they talk about their telescope. So the aperture specifically is the diameter of the objective lens or primary mirror, because as we'll see, some telescopes have lenses, some telescopes have mirrors. So if you're about ready to look through some person's daub and they say, feel free to take a look through my 8-inch daub, they're talking about the size of the primary mirror, how much light the telescope collects. So aperture, again, the diameter of the objective lens or primary mirror, is specifically and directly related to light gathering power, which is the ability of a telescope to collect light. You may have heard of telescopes referred to as light buckets. And that's exactly what they are. They're designed to collect light and bring it to a focus. So it's been a while, But let's go ahead and do a little bit of math. We haven't done a little bit of math since part two. So hopefully you remember this from, like say, basic high school geometry. But we can calculate the area of a circle by multiplying pi times the radius squared. And of course, pi is the ratio of the diameter to its circumference, or vice versa. So the area is equal to pi times the radius squared, and the radius is half of the diameter. So that's why I've made the change here. So you can find the radius of a circle by measuring its diameter and dividing by half. So notice the change we've made here. So we have d divided by 2 squared. And then we kind of work that out. So it becomes d squared divided by 4, because 2 squared is 4. So the area of a circle is equal to pi times the diameter squared divided by 4. Now, why is this important? Well, what we can do is we can compare the relative light gathering powers of two telescopes, which is the ratio of the diameters as shown here. So if we change the area to, instead light gathering power, we can divide the area of, say, telescope A and the light gathering power or area of telescope B. So the constants cancel. The pi's cancel, the 4's cancel. We're just left with the diameters squared. So we're basically dividing these two out. So we got the ratio of telescope A, telescope B, and the diameter of telescope A, telescope B squared. So for example, let's do some calculations. So how much more light will a 10-meter telescope collect than a 10-inch or quarter-meter telescope? Because the units have to be the same. So 10 meters are amongst the largest telescopes today. Maybe when I'm doing the lecture series here in a few more years, the 30, 40 millimeter telescope or 40 meter telescopes will be online, and I'll compare amateur telescopes to them. But right now, 10 meters, like the famed Keck telescopes, are amongst the world's largest. So we're going to compare a 10-meter telescope to a quarter-meter telescope, a pretty common 10-inch reflector or Schmidt-Cassegrain or something like that. So let's plug in the numbers. We got 10 meters divided by a quarter meter. So of course, 0.25 is 1/4. So the 4 in 1 over 4 goes to the top. So 10 times 4 is 40. So we do 40 squared, and that works out to be 1,600 times more light. So a 10-meter telescope collects 1,600 times more light than your common 10-inch amateur telescope. So again, bigger is better in terms of light gathering power, light gathering capacity. It's known by either term. Another important term is angular resolution, also known as resolving power. And so this is basically the ability of a telescope to reveal fine detail, because when you're observing very tight binary star systems, two stars that are very close together, or you're looking for minute details on, say, Mars or Jupiter, or even trying to spot some of the finer details in the rings of Saturn, you want a telescope that can reveal fine detail. So here's the equation for that. And this is known as Dawes limit. So you have the angular resolution, which we'll call alpha, in arc seconds. If you don't remember what an arc second is, go back and review part 2. That's equal to 11.6 divided by the telescope diameter in centimeters. Because if we're going to use the diameter of the telescope in centimeters, we have to use 11.6. Now, if you want to keep the telescope in inches, you can replace this with 4.56. So let me just tell you a little bit about this equation first, because people have asked me a lot about that in the past. So again, it's called Dawes limit, and it's named after the English astronomer William Rudder, or W.R. Dawes. And it basically describes the finest detail that can be observed through a telescope under ideal seeing conditions. And we'll talk about what seeing is here in a minute. And everyone wonders where this number for centimeters or the 4.56 in inches come from. It's not like a derived constant, like it's calculated. It was basically determined empirically, through observation by actual field testing of many and varied double stars. So this is nothing you can put pen to paper by and calculate. So it's a pretty handy system used in amateur astronomy for determining a telescope's resolution. So, for example, what is the angular resolution of that common 10-inch, or in this case, 25 centimeter telescope? Because the system we use here in the U.S. it's just awful. It's just awful. So the metric system is much better. So 25 centimeters is 0.25 millimeter or meters. It's much better. Or 250 millimeters. So it's all just powers of 10, but I digress. So we got alpha equals 11.6 because we're using centimeters, and that is 0.46 arc seconds. And remember that 1 degree equals 60 arc minutes, which is equal to 3,600 arc seconds. So 1 degree is equal to 3,600 arc seconds. That's pretty fine. And you might wonder, well, what limits the resolution of a telescope? And basically, it's something called the diffraction fringe, which is shown in this little graphic here. So this is basically a blurred fringe that surrounds any image, and it's caused by the wave properties of light itself. You can't get around it. You can lessen the effect by using a larger diameter telescope, because, of course, the larger the diameter here, the finer this detail gets. So larger telescopes collect more light, and they have better resolution. So because of the diffraction fringe, no detail smaller than this can be seen with a given aperture. And you can also check the optics of a telescope. I used to own this TMB 92 millimeter refractor. That gave the absolute cleanest diffraction fringe around stars that I have ever seen. That thing had excellent optics. I was really sad to part with it. But I just remember admiring that one night, like, man, that is the cleanest diffraction fringe I have ever seen. Now, here's what really limits your resolution in real world conditions. It's called, as we previously mentioned, seen. So this is an astronomer's term to describe the steadiness of the atmosphere, basically the atmospheric conditions on any given night. But there's another atmospheric condition we'll talk about here. So you might hear people say the scene is poor. And what they mean is the atmosphere is unsteady and it produces blurred images. Now, I'm sure we've all been in like a parking lot on a warm summer day, and you look over the roof of a car and you see it's all very blurry because, of course, there's a great deal of heat radiating outward from the roof of a car, which is why cars get so hot in the summer and why you should never leave your poor dog in the car in the summer. Now, the effect isn't nearly as bad up in the sky, but we have to look through this ocean of air above us with varying temperatures, cool air, warm air, dry air, humid air, and so on. And so ideally, when you're looking at Jupiter here, you want it to be very crisp and steady, and it is for most of its voyage from Jupiter to Earth. The sunlight reflects off Jupiter, it comes back to Earth, and most of that time, the light is nice and straight and steady and true and all that. But in that little short voyage through the atmosphere, there's basically differences in temperature and density and stuff like that. And the image of Jupiter gets distorted. It looks kind of wavy. So this is kind of a night of maybe what you would call bad seeing. You just can't ever confidently see anything. You can barely make out the great red spot here. But at least you can see the belts and the zones, but you can't really see much in the way of atmospheric detail. So that can get a little frustrating. Now, another thing that can really affect seeing is something called the jet stream, which I'm sure we're all familiar with watching the weather reports or reading about it online. And this is basically created by a convergence of cold air masses descending from the Arctic and rising warm air from the tropics. Now, you can't even see Michigan here. So, Kalamazoo, Michigan, where I am now, we're at a latitude of roughly 42 degrees. And roughly at that mid latitude, we call it the roaring 40s because the scene is never ideal here. So I can kind of back up here again a little bit. So that's why if you really want good seeing conditions, you can go further south. I've had very good seeing conditions at the Winter Star Party in the Florida Keys because the jet stream rarely ever goes that far south, and you got like 70-degree air on the land and 70-degree water, so the air is very smooth. The scene is very good. One of the best views of Saturn I ever had was from the Winter Star Party back in like 2005. And I've also had good seeing conditions at the Texas Star Party too, because again, they're higher elevation, there's less air, and they're further south. So another important term here is transparency, and this refers to the clarity of the sky. So obviously, the more transparent the sky, the more stars you can see. Now, of course, clouds, they really affect transparency. Sometimes the transparency can be zero, which it quite often is in the winter here in Michigan. But what can affect transparency on a clear night, what's really becoming common is smoke, from the forest fires we seem to get every summer now because of climate change. And then, of course, maybe on a regular night, there's basically just, for us, for example, humidity. But humidity, dust can all affect transparency. Okay, so you'll hear people refer to the transparency and seeing on a good night. They'll say, hey, it's very transparent. I can see lots of stars, but the seeing is bad. The stars are all blinking and the planetary images are all fuzzy. Okay, now for more telescope terms. Focal length. This is not as important as aperture, but it's a close second. So the focal length is the distance, usually expressed in millimeters for amateur telescopes, in an optical system from the lens or primary mirror, in the case of reflecting telescopes, to the point where the telescope is in focus, called the focal point. And so the longer a telescope's focal length, generally the more power or magnification it has. Guess what the next term is? And the larger the image and the smaller the field of view. So there's always a drawback. The longer the focal length, the more power you might have, but the less field of view. So for example, let's say we have two identical aperture telescopes. Let's say they're both 8 inches in diameter. They both have 8-inch mirrors, but one has a 2,000 millimeter focal length, while the other has a 1,000 millimeter focal length. So the one with the 2,000 millimeter focal length will have twice the power and half the field of view of the 1,000 millimeter focal length telescope. They have the same aperture, they collect the same amount of light, but they'll have different fields of view and different magnifications with the same type of eyepiece. So it's all a matter of what do you want to do? Do you want to observe deep sky objects? Then normally you might want the shorter focal length telescope, like 1,000 millimeters in this case. But if you want to observe fine details on the moon, if you want to observe double stars, or tight binary star systems, or planets, you want the 2,000 millimeter focal length telescope. Now, magnification. We all know what that is. It's basically the ability to make an image bigger. Magnification, power, magnification, it's all the same. So out of all the equations that I've showed you, a little bit in part 2, a little bit today, this is the one that you should commit to memory. The others aren't that big a deal. They just basically help you learn the basic properties of a telescope. But this one you should know. how to calculate the magnification of a telescope. Because if you share your telescope with family or the public a lot, like I do, they're going to ask you this question a lot because a lot of people think this is the most important property of a telescope. It is not. It was the first one we talked about, aperture. So here's how you calculate the magnification of a telescope. So you take the telescope's focal length and the eyepiece focal length. Again, the units have to be the same. So let's say we have a 2,500 millimeter focal length telescope. This was the focal length of my old Meade 10-inch f10 LX200 Schmidt-Cassegrain. It had a 2,500 millimeter focal length. And we'll make the math easy. Let's say I put on a 10 millimeter eyepiece. I'm going to observe some planets. And people are going to ask me, what is the magnification of this? Well, it's easy here. We just cancel this 10 or this 0. We cancel this 0, and we're left with 250 power. Now, we put the little X there. You notice there's no units like millimeters because the millimeters cancel out. So this is what we call in physics a dimensionless number. But we put this little X there to denote that it is a magnification. So with this eyepiece and this telescope, it magnifies 250 times. Now, of course, there is a limit to how much magnification you can use. I mean, sure, you could use like a 4 millimeter eyepiece. I think that maybe a 3 millimeter is probably about the shortest focal length you can find. And you can really get more power. But of course, what really limits how much power you can use is the seeing conditions, because the more you magnify the image, the more blurry it's going to get, the blurrier it's going to get. So the general rule of thumb for how much magnification you can use is 50 power per inch of aperture. Okay, so if we do 50 power times 10, that's 500 power. But in Michigan, it's really about half that. So normally on a good night around my area, this is the most magnification you can use. Now, I got to use basically this rule here when I was at the Winter Star Party in the Florida Keys, because again, the scene is much better there. So you can get close to this. And there is a rule of thumb for the minimum amount of magnification you can do, but that's more of an issue with the way the telescope is designed. You know, its focal length and optics and stuff like that. And basically, you multiply the focal ratio, which we haven't talked about yet, by 7. So if it's an f5, you multiply it by 7, and you can't use any longer than a 35 millimeter eyepiece, unless you get extensions and stuff like that. Now, the good news is you don't see stuff like this anymore. Back when I was a kid, you know, in like the 1970s and the 80s, and you're walking around your local department store, you would see, you know, Tascos and Bushnells for sale, and they would boast something crazy like this, like 675 power, which is absolute nonsense. There's no way a little tiny telescope like this, your typical 60 millimeter refractor, can ever get to 675 power and give detailed, usable images. It just isn't going to happen. I found this picture on Craigslist. Every once in a while, maybe once or twice a year, I'll just do a search for telescopes on Craigslist, just kind of see what's out, what people are selling. They're usually junk telescopes anyway. And I saw this and I thought, oh, I got to save this one to show an example of the nonsense we used to have to put up with. But you don't see this as much as you used to in department stores. They've gotten a little wiser from all the education that those of us in astronomy clubs and around the country have done. Okay, so I've mentioned focal ratio. So this is the ratio of a telescope's focal length to its aperture. So obviously, to calculate it, you divide the focal length by the aperture. So let's use the one I've been using. So a telescope with a 2,500 millimeter focal length and an aperture of 10 inches or 250 millimeters, or again, 25 centimeters, or 0.25 meters, again, the metric system, it's just awesome, has a focal ratio of 10. So 2,500 divided by 250 is 10. And this is specified as F10. Now, this isn't really important for visual use, but it can be a shorthand to refer to the focal length of your telescope. So you know that an 8-inch f5 is, quote, faster. It'll have a wider field of view and brighter kind of images than a 8-inch f10. But the 8-inch f10 will do a lot better with planetary images than an 8-inch f5. It's more important for astrophotography, but not really as important for visual use. But again, it's a great shorthand, even when talking about visual use. All right, so let's get into the different types of telescopes. And by far, the most common type of telescope, usually the one that people envision in their head, is the one in the middle, the common refracting telescope. So with the refracting telescope, also known as a dioptric, but you'll never hear people refer to it as that, you basically have a long, thin tube. Sometimes they are pretty short and stubby. Light passes through the lens, or in this case, really lenses, because you usually have at least two, and the light is bent or refracted, hence the name of the telescope. So refracting telescopes bend light and bring it to a focus, the focal point down somewhere toward the end of the tube. So it's very simple. Light goes in, it's bent slightly, and it comes to a focus. Pretty simple to draw a ray diagram of that if you're so inclined to do so. So a little bit about the refractor. It was invented most likely by a Dutchman named Hans Lippershey in probably around 1608. We know that because he tried to obtain a patent for it, but the patent office told him this was already a common design. So obviously, there were precursors to the ones Hans Lippershey tried to, patent and get credit for and all that sort of thing. So it was likely around as a toy, maybe for a couple of decades earlier. And he did file the patent on the 2nd of October, 1608, for an instrument that, quote, was used for seeing things far away as if they were nearby. Pretty good description of a telescope. And so the spectacle industry as a whole started in Venice and Florence in the 13th century. So again, the telescope was already kind of around for a while, but it was really more of a novelty item than a serious instrument. Now, the term telescope itself was coined by Giovanni da Simonani in 1611. But kind of one of my favorite names comes from the English amateur astronomer Thomas Harriot. He's kind of like referred to as the Galileo of England. He called it a perspective tube, which I always kind of liked. So here are some examples of modern refracting telescopes. And again, they come in various apertures and various focal lengths. So for example, this little guy up here, this is kind of a Televue 76 refractor. It has a pretty short focal length. So it has a wide field of view. This is great for wide field views. It would do decent on the planets too, but to really do well on the planets, you want like a longer focal length one like this beauty from astrophysics, 110 millimeter Starfire on a Mach 2 mount, which costs probably more than the cars that many of us here drive. But then there's also a nice long one like this that would give pretty decent planetary views as well. In fact, this is a pretty common size, and it's a pretty good trade-off between focal length and aperture. Has a decent aperture to where it'll do well on deep sky objects, and it'll do pretty well on the planets too. But again, they come in all shapes and sizes, but it's a matter of exactly what you want to do. Do you want something really portable with wide field use? Then a little refractor will do really well. If you want something a little bigger that'll do better on the planets, then you want something like this. Of course, the astrophysics would be nice, but, they're extremely expensive and it takes forever to get one. Okay, so let's talk about the pros of a refracting telescope. They are easy to use and reliable due to the simplicity of the design. I mean, there's not really much you can do with them out of the box. They should be ready to go. So because they are pretty much always ready to go, there is little or no maintenance. As long as you keep the dust cap over the objective lens, it should be, and keep it nice and clean, it should be good for its entire lifetime. So again, the objective lens is permanently mounted and aligned. Refractors typically don't need to be collimated. Or, the optics don't need to be aligned. So the sealed optical tube reduces image degrading air currents and protects the optics. Again, you just have to keep the objective lens covered when not in use. Use a good preventive dew system, which we'll briefly talk about later. And it should be really, really good. You rarely ever have to clean it. So refractors are really known for their high contrast images because they have no central obstruction like the reflecting telescopes we'll talk about here shortly. So again, if your main focus, pardon the pun, is with the moon, planets, or binary stars, you want to get yourself a decent focal length, nice sized aperture refractor, because that will do very well for that area. Are there substitutes? Yep, and we will meet some later. So the color correction is good in what we call the achromatic designs, and excellent today in high-end apochromatic refractors. So achromatic refractors, again, they're the low end of the refracting telescope. They use a concave flint glass and a convex crown glass because they kind of help one another in their color correction. But apochromatic refractors use like extra low dispersion glass, fluorite glass, more exotic, more expensive types of glass that really help eliminate any potential color issues. So we'll kind of get into a little more about that here in a second. So if you do have a spotting scope that you use for maybe bird watching or hunting, odds are it's a refractor. Remember, binoculars are two refracting telescopes put together. So refractors make really good terrestrial viewing telescopes, daytime spotting type scopes. Now, here are the cons of a refracting telescope. The first one is your pocketbook. They are the most expensive telescope per inch of aperture. And the cost and the bulk factors limit its practical usefulness, its useful maximum size objective to small apertures. So you never really see refracting telescopes for sale larger than maybe 6 inches. That's about the limit. They can go from like little 30 millimeter refractors, as some of the smart telescopes are today, but ones you can buy for visual use are usually in the 60 millimeter range, so like 60 millimeters, which is about 2 inches, up to about 6 inches. That's about the limit. So again, if your goal is to observe faint fuzzies, distant galaxies and deep sky objects and stuff like that, you probably don't want to get a refractor. You want to get one of the other types we'll talk about. And so, again, they are less suited for viewing small and faint deep sky objects because of their practical amateur limitations. I jumped ahead of myself there. And they are heavier, longer, and bulkier than the equivalent aperture reflecting telescopes. So, like in Michigan here at Eastern Michigan University, I've never went to go see it, but there's a 10-inch refractor. And the thing's longer than a minivan, so it's extremely long. And if you've ever been to Yerkes Observatory and visited the 40-inch refracting telescope there, that thing's in like a 90-foot dome. It's so big. And there's also a 40-inch reflector at the same observatory, and that's in a much smaller area. So because of the way refractors work, the light goes in the lens, gets bent. They tend to be very, very long in larger aperture, longer focal length designs. So that's why they're limited to smaller sizes. And as they do get big, they get really expensive. So They are difficult to collimate if the optics are knocked out of alignment. Very few refractors can be collimated by the user. They don't really offer that ability. So if you do have a nasty accident with your refractor, you drop it on the ground and knock the lenses out of whack, you usually have to send it back to the manufacturer, and that could be, hundreds of dollars in shipping costs, to and from, and also the cost for them to do it. So again, treat your refractor very, very carefully. And of course, there is some color aberration, or sometimes a lot, in the achromatic designs, which have a doublet lens. Again, they have flint and crown glass together. So let's talk a little bit about chromatic aberration. So every lens tries to act like a prism. Prisms break light up into its constituent colors on purpose, but refractors do it because they just can't help themselves. So in this case, though, we have a single lens, just one type of lens. It could be made of flint or crown glass, whatever. And so the white light comes in, and we all know from prisms, white light is made of many colors, mainly red, green, and blue. And so in achromatic refractors, they only focus the red and blue light. They might not be quite this bad, because again, that's what the two lenses of different types are for. They help correct one another, and they can bring the red and blue light to the same focus. But in this case, we're using a single lens, and the red and the green and the blue do not come to the same focus. So here's what this looks like through a telescope in an achromatic refractor, where the red and the green do come to a focus, but the blue does not. It kind of looks like this. I can never find a decent image of a planet like this, but there are plenty of images with stars. So here's a nice image of the Andromeda galaxy and one of its satellite galaxies. And you see what we're trying to focus on here, though, are the stars. Notice they all have these little purple halos around them. This is called a secondary spectrum. And so this is one of the causes of chromatic aberration. So all the colors of the spectrum are not coming to the same focus. Now, there are like minus violet filters you can buy to correct for this, but still, it obscures it. It's not solving the problem of bringing all the colors to an identical focus. Now, apochromatic refractors have pretty much solved this problem. And this has plagued astronomers since the 1600s. Their solution was to make some telescopes very long focal length. You can see historical like sketches out there of them. But today we use more expensive exotic types of glasses that do bring all the colors of light to a similar focus, but it usually is pretty expensive. It's getting cheaper now because of imports and stuff like that. But still, apos can be or usually are quite a bit more expensive than achromatic refractors. But again, the price has come down significantly in the past decade or so because of the imports from China and so on. Okay, the next type is the reflecting telescope. And there are many different types of reflecting telescopes. The specific one shown here is a Newtonian reflector, invented by none other than Sir Isaac Newton himself in 1688 as part of his miracle year, when he was sent home during a pandemic and had a lot of time on his hands. We kind of have a little experience with that now. So you can see here, it's a little more complicated. So the light comes in. It is not bent or refracted in any way because there's no lens up front, basically a big opening. You can stick your hand right in here if you want. And so the light goes straight in, as you can see here. But notice the mirror is a concave parabolic mirror. So when the light reflects off the mirror, it does so at an angle shown here. And then it reflects off this flat secondary mirror at a 45-degree angle. And you can see eventually the light here will kind of crisscross. They'll cross one another, and it comes to a focus. So a little more complicated than your typical refractor, but still not so bad. The light goes in, reflects off one mirror, reflects off the other mirror, and up to the side of the telescope here. So here are some typical Newtonian reflecting telescopes. And this is probably the most widely type of amateur telescope used, but I think refractors are catching up because of the smaller imports now, especially for astrophotography. So you can again see they come in a wide variety of apertures and focal lengths. So this is a little 76 millimeter tabletop telescope, very short focal length, so pretty wide field of view, very portable too. Makes a great display unless someone steals it from your storage facility, but that's a problem that we had recently. And so like this one here from Sharp Star, this is specifically designed for astrophotography. So it's very fast, a low F ratio. So it has a large secondary obstruction here. Not great for visual use, but ones like this one here, this one would be really great for visual use. But maybe this one too from Vixen, but this one here from Astrotech. This one's specifically built for astrophotography, but with the special extensions, you can use it for visual use too. I have one of these that I've heavily modified with new focusers, new collimation knobs, and stuff like that. But I've never used it for visual use. And you've probably seen the legendary Astroscan from Edmunds Scientific, and this is also a little Newtonian reflector, but does have a little corrector up front because it is so short. So let's talk about the pros of the reflecting telescope. Again, the bonus this time is your pocketbook. They are the lowest cost per inch of aperture because they are so easy to make. In fact, they are so easy to make, a lot of people still choose in this day and age to ground their own primary mirrors. So for a long time, people had to do that by necessity, grind their own mirrors, shape them just right, get them aluminized and all that sort of thing, because it was much more affordable to do it in like the 1930s and 40s and 50s and even into the 60s. But now, because of imports, most people choose not to build their own telescopes anymore. That's becoming kind of a lost art, but many amateurs still do it today. So because they are so easy to make, they are available in the widest range of apertures. Again, they can come as small as 76 millimeters, roughly 3 inches, up to roughly a 30-inch monstrosity available today. There used to be ones a bit bigger than that, but I think the limit today that you can purchase is roughly 30 inches. That's reasonably accurate. So again, if your focus is going to be on looking for the deep sky objects, the faint fuzzies, as we call them, you want a nice big telescope. And one of the most ideal ones for the purpose is a good Newtonian reflector, because they are excellent for faint deep sky objects, such as nebulae, star clusters, and especially galaxies. They are low in optical aberrations and deliver very bright images. They have no issues with chromatic aberration because they don't have any lenses. The only lenses in the system are in the eyepieces, and they don't really cause much in the way of chromatic aberration. Nothing that you can see anyway. And the longer focal length ones, like say an f6 or f7, they are still pretty good for the moon and planets. You can get longer focal length ones or build one, but they're usually very, very long and not very portable. But your typical 8-inch f6 will do a really good job on the moon and planets. As big as an equivalent aperture refractor? No. But they will do a pretty respectable job, absolutely. And again, they are reasonably compact and portable up to focal lengths of about 1,000 millimeters. Because again, we do use the term backyard amateur astronomer, but many of us can't observe in our backyards because of light pollution. So we usually have to travel somewhere where it's reasonably dark, or really far if you want really dark skies. So your telescope has to be portable too. There has to be a balance between aperture, and portability. and of course cost too, but hey, just donate your blood or something. It'll be fine. So the higher end models like that Sharp Star are excellent for deep sky astrophotography. So some of the best images you'll see out there are taken with large aperture, short focal length, or fast Newtonians. Now, here are some of the cons. They are not suited for terrestrial applications. You will not see any spotting scopes that are Newtonian reflectors because they show everything upside down. So who wants to look at a bird in a tree upside down? So Newtonian reflectors specifically are astronomical telescopes only. And that kind of bothers amateurs a bit, especially when you look at the moon, because you'll really notice the moon will look upside down. But as we just tell people, get over it. You can correct for that, but it kind of degrades the image a little bit. So for observing stars, you don't want that, or deep sky objects. You want a good, clean image. So for a daytime scope, get yourself a refractor or the next type of telescopes that we'll talk about. So the open optical tube design does allow image degrading air currents and air contaminants. So if you do use your Newtonian a lot outside and it gets dewy and eventually dusty, you'll have to take out the primary mirror and clean it, which isn't really all that hard. You can just basically start by pouring a gallon of distilled water on it and kind of build up a solution with distilled water and alcohol, and that'll clean it up. There's plenty of examples out there of instructions of how to clean your primary mirror, but we're not going to quite get into that today. But it can be done pretty safely, but it's not something you really have to do very often, though. So that's kind of the good news. And there is that secondary mirror in the way, so there is a slight light loss and a bit of loss of contrast in Newtonian. So again, a 6-inch refractor will always outperform a 6-inch reflector because of that secondary obstruction in the Newtonian. You can't get around that, at least with the Newtonian design. So they do require frequent collimation. I mean, you have to tune your violin, you have to tune your piano, you're going to have to tune your telescope. Now, refractors, not very often, if ever. Newtonians, especially the big ones, every time you take them out. Every time you take out like a large 8-inch, 10-inch, 12-inch, or bigger Newtonian, you're going to have to collimate it, especially for astrophotography. It's much more stringent than visual use. Now, Newtonians do suffer from what's called off-axis coma, where stars look like little comets toward the edge of the field of view, but there are devices called coma correctors that basically eliminate that. So again, any aberrations Newtonians have are easy to correct, but you have to get yourself a coma corrector. It's not so big of a deal for visual use, unless you're really, really picky. But for astrophotography, it's really important to have a coma corrector for especially a fast Newtonian like an f4, especially an f2. And again, the large apertures over 8 inches do become kind of bulky and heavy, and they do tend to be more expensive. Not as bad as a refractor that size, but still pretty pricey and not terribly portable. But there's a way around that, and we'll see that shortly. Now, our final type is a catadioptric telescope. And the one shown here in the picture is a Schmidt-Cassegrain. We'll also briefly look at a Maksutov-Cassegrain too, but I don't have any spiffy pictures of it, but they look very, very similar. So you'll notice the tube in this case is kind of short and stubby because Schmidt-Cassegrains do look a lot like light buckets. They literally are, do look like light buckets more than any type of telescope. It's like a bucket with mirrors in it, So the light does pretty much go straight in, but there is this thing up front called a corrector plate because it's so thin. But what it really is, it's a lens. It's a correcting lens. But again, it's so thin, we call it a corrector plate. So when the light does come in here, it is slightly bent like a refractor. So that's why Schmidt-Cassegrains like this are known as hybrid telescopes. They have properties of a refractor in terms of the light getting bent here, and mostly of a reflector because they have mirrors. So the light comes in, bounces off a kind of spherical primary mirror, because if you draw the whole thing out, it'll make a big old circle. So reflects off the primary mirror up to the secondary, which has a bit of a curve to it, and then out through an opening in the center of the primary. Yeah, so the primary mirror of Schmidt-Cassegrains and Maksutov-Cassegrains, they have a hole right in the center. And, why not? Because it's in the shadow of the secondary anyway. So, why not put a hole there? So the reason to do this is to make it much more compact and portable. So Schmidt-Cassegrains came on the scene in the early 1960s thanks to Tom Johnson at Celestron, who again was the first to market these in the early 1960s because people wanted more portable telescopes because throughout the 1950s, streetlights became much more common. So there went their nice, wonderful dark skies. So people began to travel outside of their city looking for dark skies. And you didn't want to bring your giant refractor or reflector with you. So you wanted something more portable. And yes, Schmidt-Cassegrains are very portable. Now, they are maybe kind of an endangered species because only two companies made them, Meade and Celestron. There were others like Criterion, but Criterion is long gone. And now Meade is long gone. I've taken out all the Meade telescopes I used to show here because they are no longer viable. They are gone. So the only maker of Schmidt-Cassegrains that I know of are from Celestron. So once they go, if they do go, I don't know if they're going to or not, I think the Schmidt-Cassegrain may go with it. For visual use, they're very fine, but people tend to prefer refractors or Newtonians for astrophotography. I mean, yeah, these are really marketed toward the astrophotographer, but a lot of people, again, prefer the other types of telescopes specifically for astrophotography. So again, they all have this kind of short bucket design, and they come in various sizes. Roughly, they start at 4 inches, and now they only go up to 14 inches because Meade used to make a 16-inch, but again, they're gone. As far as I know, there's no more 16 inches being made. So just from 4 inches to 16 inches, because as they 14, 4 to 14 inches, because Celestron does make a 14-inch. This is probably an 11-inch here, but I forget. It looks like an 11-inch. Now here are some Maksutov-Cassegrains. They are very similar to Schmidt-Cassegrains, but instead of a thin corrector plate, they have a thicker correcting lens that has a bit of a curve to it. When you look at them in person, you can kind of get a sense of it here. The correcting lens has a clear curvature to it. Now, these are usually longer focal length than an equal Schmidt-Cassegrain. There aren't really any 7-inch Schmidt-Cassegrains. Let's just say there is one. So let's say you compare a 7-inch Schmidt-Cassegrain to a 7-inch Maksutov-Cassegrain. The 7-inch Mac, as we call it for short, will have a longer focal length and thus a higher F ratio. Like the 7-inch from Celestron is a F15, while usually most Schmidt-Cassegrains for visual use are F10s. There are some F6.3s out there for astrophotography. At least there used to be. I'm not sure. I assume Celestron offers some, but I'm not really sure 100%. Meade used to, but they don't exist anymore. So I recently got myself a 7-inch Meade Maksutov, and they are excellent for planetary use because a big Mac, like a 7-inch Mac, will nearly equal a high-end refractor in terms of resolving power, color correction, and so on at a fraction of the cost. And they're also much more portable. So if you don't want to break the bank and get yourself a high-end 6-inch, 7-inch refractor for planetary use, try getting a big Maksutov. from like Celestron or Ioptron. I know the one from Celestron is specifically a 7-inch here. This is a smaller 102 millimeter, like 4 inches. And I think this is 105 millimeter there, so a little bit bigger. But these are great. And you've probably seen the scopes from Questar. They're constructed of titanium. The whole tube rotates on there. It's very, very cool. The old Meade ETX 90 was kind of ripped off from this design. But these are ungodly expensive if you can find one today. I'm not really sure if they're made new, but you can find some out there used. And boy, even back in the 70s, these things sold for a couple $1,000s. So the Maksutov was invented by Dmitry Dmitrievich Maksutov in 1944 in modern day Ukraine. And they are, again, excellent. They're kind of becoming more popular than they used to be because they also make really good spotting scopes too. Like this little booger here can be put on a standard camera tripod and be used for a spotting scope if you use a 45-degree diagonal as opposed to the 90-degree one that it comes with. Okay, so let's talk about the catadioptric pros. Now, some consider them to be the best all-around, all-purpose telescope design. I mean, they do really well for deep sky objects and larger apertures. So a 10-inch Schmidt-Cassegrain will do pretty good for deep sky objects, but a 10-inch Newtonian is usually a little better because the images will be a little bit brighter because of the smaller central obstruction. And usually Newtonians are faster than Schmidt-Cassegrains. But the Schmidt-Cassegrain will be a lot more portable, even though it's actually a little heavier. Now, so they do have excellent optics with razor-sharp images over a wide field of view, especially the latest ones from Celestron, like their Edge HD line they came out with probably about 15 years ago now. And they still do a pretty good job for the moon, planets, and binary star observing. So again, if you can't really afford a high-end refractor and don't want a giant Newtonian, a Schmidt-Cassegrain has plenty of good trade-offs. You know, they still do pretty good on deep sky and pretty decent job of the planets. And again, they are good for deep sky observing or astrophotography. Now, again, they do have a closed tube design that reduces image degrading air currents. The only thing you might have to do is make sure you clean the corrector plate for Schmidt-Cassegrains or the correcting lens for a Maksutov-Cassegrain once in a while. I currently have a 9¼ inch Schmidt-Cassegrain, and I've had it for quite a while. I don't use it as much right now as I used to, and I've never had any reason to clean the corrector plate, even when I was using it heavily. But I don't use it much right now. But we do have a 16-inch scope in our observatory here in town. And, you know, when we're not using it, we keep it covered up. We're always running the anti-dew system when it's in use. So we've had no reason to ever clean the corrector plate. And we've had it for a good 6-7 years now. And as I mentioned, most are extremely compact and portable. That is the whole purpose of the design for Schmidt-Cassegrains. Maksutov-Cassegrains are just a little bit longer, but they're usually smaller size anyway, so that kind of balances out. And they are pretty durable and virtually maintenance-free. You don't have to collimate your Schmidt-Cassegrain every time you take it out. But eventually, you will have to collimate your Schmidt-Cassegrain. But you only do that with the little hex screws up front with the secondary mirror. But you can replace those with something called Bob's knobs, and that makes them really easy to collimate. As soon as I got my 9¼ I replaced the screws with Bob's knobs. As soon as we got our 16-inch at the Nature Center here in town, we replaced it with Bob's knobs. They're really cheap, and they make collimation much easier, and there's no chance of using the tool and slipping and scratching your corrector plate. Now, here are the cons. They are more expensive than Newtonian reflectors of equal aperture. And just like with Newtonians, but a little more severe, there is a slight light loss due to the secondary mirror obstruction. You know, so some of the light going into the tube is being blocked by the secondary, and that that decreases the contrast of the image a little bit. And because of all the glass they do take longer for the optics to reach thermal equilibrium. Because we talked about bad seeing, the differences in temperature in the atmosphere. Now, if you bring your telescope from inside where it's 70 degrees to outside where it's like 50 degrees, maybe in the summer, or even worse in the winter, your telescope will give off heat for a while and cause seeing issues in the optical tube itself. So you have to give the tube time to reach thermal equilibrium to have the temperature match that of what it is outdoors. But normally, if you set up your telescope, 20, 30 minutes early, it'll be fine. It's a little worse for Maksutov-Cassegrains, but not much more so. And the most notorious thing is the way they focus. When you turn the knob, you can't really see the knob here on the image on that I have here, but when you turn the focus knob, that moves the primary mirror back up and down this baffle, right? And so, especially in larger apertures like a 8-inch or especially 10-inch and 12-inch, um, the mirror will shift a bit, and you'll see the image bounce around, and that can be kind of frustrating when you're trying to reach a precise focus, for planetary observation or looking at a very tight double star system. Now, the current 16-inch that we had replaced a 12-inch Schmidt-Cassegrain we used to have, and that thing had the worst mirror shift over time. It just got worse with age. And not only did it have image shift when you were focusing, but when you did focus, the mirror would like slide back a bit and you would lose focus. So with that old Meade telescope that we had, it just got worse with age. And with the current 16-inch, we have a dedicated focuser on the back. So we no longer turn the little knob to focus it, at least not very often. And most Schmidt-Cassegrains are F10s. So they do have a narrower field of view compared to a fast Newtonian. So again, if you're looking for something to scan the skies, looking for deep sky objects, it'll be a little easier in a Newtonian because of the more generous field of view. And large apertures, 10 inches and up, are pretty heavy. You can set up a 14-inch in the field, but it can be difficult, especially if you're not a large person. If you have a smaller frame, you'll have a difficult time with a 14-inch. But put it in an observatory, and who cares? You can just hire someone to put it on the mount one time, and you never have to worry about it again. But the old Meade 16-inch on a fork mount, man, that thing was really, really heavy. So you need help setting that up. So now let's go ahead and dive into telescope mounts. We'll do a little bit more of this in part 5 on astrophotography. So today we'll talk about just kind of the basic types of telescope mounts that are out there today. So the first type we'll talk about is a German equatorial mount. And you can see there's a Schmidt-Cassegrain on that mount there from Celestron. So what you have here is a telescope on one end with a counterbalance on the other. So that can be part of the reason that makes German mounts a little difficult to transport out into the field, because you usually have to bring at least one or more counterweights with you. And again, they're kind of, some are 10, 20 pounds. So they're a little difficult to bring with you in the field sometimes. And you'll notice the entire mount is at a bit of an angle. So imagine like a nice horizontal line here. And you'll see the mount is at a very specific angle. And that angle is based on your latitude. So, for example, Kalamazoo is at a latitude of 42 degrees. So this mount looks like it's roughly at a 42-degree angle, probably a little less than that from the picture, but you would want this mount at a 42-degree angle, in Kalamazoo, Michigan. And also this end here, where you see this little cap here, pointing this way, that has to point toward the North Celestial Pole. So German mounts have to be set up in a very specific way. They have to have one specific end pointed toward the North Celestial Pole, right near Polaris. And you have to have the whole mount tilted at a specific angle based on your altitude or latitude or the altitude of Polaris. So again, the mount basically moves in right ascension. There are usually little motors kind of in these little boxes here that turn gears that make the thing move in the opposite direction the Earth is rotating to keep stuff within the field of view of your eyepiece or camera in some cases. And it also moves in declination, which basically means the whole thing kind of spins around on the mount. I mean, one of these days I'll try to make an animated version of this where you can see it move, since we're not here doing this in person. So again, German mounts, they're really, really great. They're really easy to set up. They're easy to polar align, easy to balance, just not terribly portable. And you do have meridian issues because when you do cross from the eastern sky to the western sky when you're tracking something, you have to do what's called the meridian flip. Otherwise, the mount doesn't usually track very far when the scope is horizontal or less on one end, and the counterweight's starting to kind of stick up here in the air a bit. Now, some higher end mounts don't have that issue; they can track for hours past the meridian, but you have to worry about your telescope bumping into the tripod as well. So a few basic facts on a German equatorial mount for you. I lay out, I think, the pros and cons a little bit better in the companion guide. So be sure you check that out too. So with that bit of knowledge, it just makes this advertisement all the funnier. I got this from Terence Dickinson, the late great Terence Dickinson, the author of Night Watch. And he shared this when he visited us during one of our anniversary years back in 2011. And it's just ridiculous. This is an advertisement in a Sears, for Sears in some newspaper. And it just so shows everything wrong that the layperson gets with the telescope. So, number one, this is a Newtonian reflector. So the light is supposed to come in here. And here it is pointed at the ground. The finder scope is on backwards. So remember, light is supposed to come in here, but they're looking through the eyepiece of the finder scope there, and it's pointed the wrong way. It's supposed to point in the same direction as the telescope. And the equatorial mount, maybe they are at the equator, but it doesn't look like it, and that's what they're set up for. So the mount's set up wrong, the telescope is set up backwards, and the finder scope is on backwards. And it's not even 450 power, of course. That's ridiculous. I mean, yeah, you could get 450 power on this thing, but could you see anything with it? No. So it's just a completely ridiculous ad that shows everything wrong here. Now, another mount that's on the rise, these things first started coming out in like the mid 2000s, like 2004, 2005, but the first batches were large mounts. But they really began to hit their stride in popularity with the smaller portable versions shown here. So these are harmonic drive mounts, also known as strain wave mounts, but I don't like that term, strain wave. It sounds like some kind of virus to me. So I've always preferred to call them harmonic drives. And they're basically harmonic drive mounts use advanced strain wave motors to create ultralight, ultra portable, and ultra accurate mounts for a pretty reasonable cost. The first portable ones came from Rainbow Astro, and that's the one shown here. And they do have several models. This is specifically the RST 300. That's their most expensive one, though. That thing can hold up to 66 pounds without counterweights. They do have a weight limit with counterweights, but why? I'm not going to mention those. I didn't make any notes of it because if you're using these things with a counterweight, why didn't you just get a German equatorial mount? They're in some ways superior, they're cheaper, And the whole point of the harmonic mounts is you can use them with no counterweights, at least for smaller size telescopes. Putting a massive 14-inch Schmidt-Cassegrain on here would make me very nervous because when the thing's kind of tilted over to the one side of the sky, the whole thing could tip over unless you got a really beefy pier that this thing is bolted to. So they do have other mounts, but they are pretty expensive. There's an RST 135 that holds 30 pounds. That's about $4,200. There's an RST 135E that has absolute encoders, so you don't need auto guiding. That's not really important for visual use, but those sell for nearly $6,000. And this one here's are nearly $9,300. So they are very expensive. Much more affordable and much more popular, of course, are the ones from ZWO. They first came out with the AM5, but now there's like an AM5N, and they all have an N after it now, so I'm not going to bother to mention that. But there's an AM3, an AM5, and an AM7. The AM3 holds up to 17 and a half pounds with no counterweight, and those are about $1,700. The 5 holds up to 33 pounds, and that holds up to 33 pounds. I think I said that, 33 pounds for $2,500. And the AM7 holds up to 44 pounds and sells for about $3,000. This one is so new, as of the time of recording here, it hasn't even shipped yet, I don't think. But the original AM5 has been out for several years now, and some of our members have one, and they've been doing excellent astrophotography with it. So you can use them for visual use. They're all go-to, obviously, and they're great. Now, there's these ones from Ioptron, but boy, you go to look at the Ioptron website to get info about these, and there are so many different variations that it gets really confusing. I mean, it's so simple from ZWO. They got the 3, the 5, and the 7, but with each of these, there's like different versions. And one of them, like the 29, I forgot to update the labels here with the newer versions because they kept changing those things. But this is equivalent to the HAE 29B, which is about $2,600 and holds 29 pounds. The great thing about the Ioptron ones, by the way, is they can be configured for either azimuth or equatorial mode. So that's really great. I think some of the rainbow ones can too, but I'm not 100% sure on that. So these are becoming very, very popular because, again, they're highly portable and they don't require counterweights. Now let's talk about the all azimuth mount. Now that's kind of the short version. So really the full version of the name is altitude azimuth mount because they move in altitude and azimuth. Altitude, they move, basically the tube moves up and down. Azimuth means they spin around in different directions. So for the beginner, all azimuth mounts are much more intuitive because with the German equatorial mount, the whole mount's tilted at a specific angle, and they don't move in a kind of a intuitive type of way sometimes, at least not at first. But all azimuth do right out of the box. They're very easy to move. They move left, right, up, and down. Very simple. Now, there weren't too many all azimuth mounts when I began my journey as an amateur astronomer years ago, but now there are quite a few out there, and many of them, like the ones from Skywatcher or Ioptron, have go-to capability. But there are plenty of nice manual all azimuth mounts out there now too. If you really like well-machined mounts, then you can get yourself one of the AZ8s from Los Mandy. It has a dual mounting system. You can have, like, say, a Schmidt-Cassegrain on one side and a refractor on the other, and they do hold a lot of weight too. They're really bulky, but really, really well made, really well machined. Now, the absolute most popular type of all azimuth mount is the Dobsonian mount. In fact, the design is so prevalent, many people think a Dobsonian is a different type of telescope. But a Dobsonian telescope is a Newtonian reflector on a rocker box style all azimuth mount. That's all it is. And they come in a variety of sizes, basically as small as, like, again, like 4 inches, like a tabletop telescope, and to monsters that we'll look at here briefly. Now, if you ask me, well, hey, Richard, I don't have time to look at all these telescopes. Just tell me which one you think I should get, right? So, if you absolutely want to buy a telescope, don't want to do a lot of research, get yourself a 6-inch or 8-inch Dobsonian. You'll be able to use it for years for visual use. You just can't use them for astrophotography. If you want a good telescope for astrophotography, well, join us for part 5 and you'll find out then. Now, I used to highly recommend the Orion Dobsonians because when I sold telescopes years ago, I sold lots of those things. But Orion is gone, and they took Meade and Coronado with them. Now, there's ones from the company Apertura. I probably say that wrong a bit. It's a confusing name to me. They're now the kind of the successor to the old Orion Odyssey or Dobsonians. So they do make very nice either 6-inch or 8-inch Dobsonians. So if you're looking for your first telescope, I recommend one of those. They do the deep sky objects really well. They'll do the planets really well, but they don't have any of the bells and whistles. But you can get go-to versions. Now, I do really like the Skywatcher flex tube Dobsonians because the upper portion here, it extends outward. We purchased one of these, we as in the Kalamazoo Astronomical Society, for loan to our members. So if you are a KS member and live in Southwest Michigan, you can borrow the 8-inch version of this one. This is the 10-inch here. You can see it's $250. So that means it's the 10-inch. And Explorer Scientific has some monster ones too, because I mentioned one of the cons for a Newtonian is when they get to larger aperture, especially if they have a solid tube, they are not very portable. But I mentioned there was a way around that, and you can see it here. You have a truss tube design. And so that has caused Dobsonians to get very big, or at least, maybe caused, but enabled them to get very big, where you can get monsters like this from a company called Obsession. So here we have two 25-inch Dobsonians. Can you imagine how heavy these things would be if they had solid tubes? You can't really tell because they have shrouds, but you can see the outlines of the truss tubes pretty clearly. And this is a 20-inch. Now, I've never looked through a 25, but one of our members who, when he lived in the area, allowed me to look through his 20-inch, either in town or at a couple of star parties. And there is a problem when you look through a big Dob like this. There's a huge contagion that you should know about. Okay, this is very serious. So when you look through one of these gigantic Dobsonians, you get something called aperture fever. I mean, you look through one of these and you're like, I have got to get me one of these because some of the images are just out of this world, literally. I mean, awesome. But I have the cure for aperture fever, and it is called poverty. So I can't afford one of these things if I wanted one, which I would love to get one. A 20-inch, I think, would be really, really great, but I can't afford it. I should charge more for stuff like this, which is, of course, right now free. But here's just a little story. Is with that member, his name was Robert Wade. He's now retired in New Hampshire. And we were both at the 2005 Winter Star Party in the Florida Keys. And he pointed his 20-inch Obsession at the grandest globular cluster in the entire sky, Omega Centauri. And he was using a 31 millimeter Nagler Type 5 eyepiece, you'll see one later, with a 2x power mate. And when I walked up to the eyepiece and looked through it, I screamed I was so amazed at what I saw. I screamed an obscenity. I said, holy, and you can fill in the rest yourself. And people just came around. They're like, what's wrong? What's wrong? And Robert was just like, oh, it's just Richard. He looked at Omega Centauri through my telescope. And of course, everyone's like, I got to see that. And it was just the most amazing, incredible view ever. The entire field of view was filled with this tens or hundreds of thousands of stars. It was incredible. Now, when I was at Okie-Tex Star Party, where this picture was taken, I wish I would have walked over one night to look through this guy's 30-inch obsession. I don't even think they make a 30-inch anymore, but I didn't do it, and I still regret it to this day. So, oh, look at that monster. Oh, it's a beauty. Now, I have looked through this telescope. This is famously called the Yard Scope. It's a big 36-inch Dobsonian. I don't know what ever became of it, but back then anyway, it was owned by a guy named Crazy Bob Summerfield. I don't know if he's still active in amateur astronomy, but I looked at M51 through this telescope at the 2001 Texas Star Party. It looked like one of the sketches from Lord Ross using the Leviathan of Parsonstown, a giant Newtonian in Ireland. And I also looked at the Horsehead Nebula here at the Winter Star Party. Obviously, this isn't Texas with the ocean and the palm trees. You could clearly see the horse as plain as day. The only time I ever clearly saw the Horsehead was through a big Dobsonian like this. Now, the biggest one that I've heard about, I've never seen it, is Mike Clement's 70-inch or 1.8 meter Dobsonian, which I believe is still the world's largest backyard telescope. Again, I have no idea if it's still out there today or it's just sitting in some storage facility or his basement or garage or whatever. But I would love to look through this. I mean, yeah, you'd have to climb a pretty tall ladder, which I don't see in the picture anywhere, but he obviously has to have a tall ladder to get up to the eyepiece up here somewhere. But I would certainly do it. It'd be worth it. If I fall off the ladder, I'd be very happy until I at least hit the ground. Now, kind of a little joke here. Dobsonians do have one other great use. And again, this is from the 2010 Okie-Tex Star Party, is they can give you shade during the day. So there you go. That's a great plus right there, because you're usually out in the open in the field, good observing spot. You have no shade, but if you got a big Dob with a cover, problem solved. There you go. But just remember, the whole point of these big monster telescopes is the larger the aperture, the brighter and sharper things become. So this is your typical view of the globular cluster M13, the best globular cluster in the northern skies, through an 8-inch Schmidt-Cassegrain again. But the larger the Dob, the larger the telescope, the brighter and sharper those objects become. So, I mean, aperture is kind of everything, but not everything, There's still cost, portability, you have to store it somewhere, and so on. So take all those factors in and pick out the telescope that's right for you. So here is some purchasing advice. Number one, the whole point of this series is to educate yourself. That's why you're here. I assume you're all here to learn. So educate yourself. Attend series like this. Maybe your club has another version or will come out with one to match this one. Read, do research, learn, keep learning. I've been doing this for over 40 plus years. I'm still learning stuff all the time. It never stops, and that's the fun part of it. Join your local astronomy club and attend their observing activities, observing sessions, open house, public nights, star parties, whatever. If your club sets up telescopes somewhere, go to those events, join the club, support them, and learn as well there, because you can learn a lot more looking through these telescopes in the field than you can on a showroom floor or on pictures on the internet. So if you do have a local club, join it and attend. Maybe you can't attend every activity, but if you love amateur astronomy, you should support your local astronomy club. Take advantage of your club's telescope loan program if you have one. The Kalamazoo Astronomical Society does have one. We have several telescopes to choose from. We do have a smart telescope now. We're going to talk about those today. We have a big pair of binoculars. We have a nice 4-inch refractor. We have that 8-inch Dobsonian. We have an 8-inch Schmidt-Cassegrain. And we even have a nice dedicated solar telescope as well. So many telescopes have loan programs like we do, but of course you have to join. It has to be local. So you can check it out because, yeah, if you join our club from California, we're not going to ship it to you. You have to be local, and not just local club events, but attend, big star parties like I've mentioned, like the Texas Star Party, the Winter Star Party, the Nebraska Star Party. In Canada, you can go to Starfest or the Saskatchewan Summer Star Party. I tried going to that once, and the weather was terrible, but I hope to go again someday. And read reviews. People post reviews on the blogs of their website, or on magazine websites like Astronomy and Sky and Telescope. They publish them, of course, in the magazines themselves. So again, read reviews. That gets back to educate yourself. But the one thing you should really, really remember from today is never ever buy a telescope at a department store like nationally, like Walmart. They are all, without exception, garbage. You will throw your money away. Do not buy a telescope at a department store. Buy it from a reputable dealer, and if you have the opportunity, a knowledgeable salesperson. Most of us are going to buy it through a website without ever speaking to anyone. But if you do, like, have a telescope shop in town, one of the first things you should ask the salesperson is, what telescope do you own? And if they say none, they don't know what they're talking about. They probably learned something, on the job. They don't know what they're talking about. All right, now let's talk about the wide variety of telescope accessories. The most common accessory is this big old thing on the back there. Eyepieces. For visual use, you want at least 3 of these things. Most telescopes come with at least 1, maybe 2, but it's good to get a whole collection. I can't tell you how many eyepieces I have now. It's got to be well over a dozen. Do I use all of them every night that I go out? No, but I have them when I need them. So it is good to have a wide variety of eyepieces. Now, the standard today is 1.25 inches. It's been the standard for decades, a long time. There are still some department stores that come with the 0.965-inch diameter barrel eyepieces. These are the diameters of the barrels on the eyepiece. So if the eyepiece barrel is roughly 1 inch across, or about the size of a quarter, don't get it. Pretty much all 0.965-inch eyepieces are garbage. So don't get one. 1.25 inches is the standard, and 1.25 inch eyepiece will work on any telescope. Any manufacturer eyepiece will work on any other manufacturer's telescope. That's what's so great about it. You don't have to, buy a Skywatcher telescope and buy Skywatcher eyepieces. You can buy a Skywatcher telescope and get TeleVue eyepieces. That's my personal preference, because Uncle Al was such a great guy, Al Nagler, and he was always gracious to me when I met him. So, and I loved the eyepieces too, just to boot. So I was very happy to have pretty much quite a few TeleVue eyepieces myself. So, if you want really wide field views, then you can get yourself a 2-inch eyepiece and get some of the really ultra wide field field of view eyepieces like Nagler's and Ethos and stuff like that. They are expensive, but boy, are they good. Now, there are some 3-inch eyepieces out there. I believe only Skywatcher, I think it's them, that makes a handful of 3-inch eyepieces. And you also have to buy a 3-inch diagonal, but I don't know. That just seems really unnecessary to me. 2-inch eyepieces have always give you more field of view than you can need, especially with an Ethos style eyepiece. You have to move your head around, to take in the whole field of view. So 3 inches, it's kind of a cool novelty thing, but I don't think really necessary. So, real quick here, let's go through the different types of eyepieces that are out there that you might encounter. The first type of eyepiece, in fact, the first compound, or multi-lens eyepiece was invented by Christian Huygens in the late 1660s. It has two elements, a pretty narrow field of view. They can be good for solar projection just because they're so simple. And they are now, though, an obsolete design. So if you do see an eyepiece with an H, they're usually 0.965, but there are some inch and a quarters out there like this one that might have an H on it. That denotes it's a Huygens eyepiece. Again, if you do a lot of solar projection, I mean, sure, why not use it? But otherwise, you want to reject it. Then kind of a variation of the Huygens eyepiece is the Ramsden eyepiece created by someone named Jesse Ramsden in 1782. This also has two elements, similar field of view. They are lightweight like the Huygens with moderate field curvature. And again, obsolete design, pretty much for solar projection if you can find one. They'll have like a little R on them somewhere. Now, when I started amateur astronomy, now decades ago, the Kellner was considered the base eyepiece to get, but that's no longer the case anymore. So these were designed by Carl Kellner in 1849, and this is the first modern achromatic style eyepiece with different lens elements inside, which it had three of them in all. The field of view was a little more larger, which was nice. They weren't very expensive then or now, and they do still have some field curvature though. And so if you see a KE, that denotes it's a Kellner eyepiece. Again, maybe good for solar projection, but there are better ones for visual use that don't cost that much more. And they're so obsolete now, they're getting hard to find. Now, still pretty good today by today's standards are orthoscopic eyepieces. These were really commonly sold by a company named University Optics in Ann Arbor here in Michigan. And so for a while, these were kind of considered the high-end eyepieces. They have four elements, again, a 45 to 50 degree field of view, which is pretty good. Excellent contrast, but with some internal reflections. These were invented by Ernst Abbe in 1880. So again, they've been around for a while. Now considered the standard today, the minimum style eyepiece you should get is a Plossl, designed by George Simon Plossl in 1860. And these became very popular in the 1980s when Televue began to sell the first serious line of Plossl eyepieces. They still have a more updated version today. I just got myself a 40 and 32 millimeter to use with my 7-inch Mac. Because it doesn't really work with 2-inch eyepieces very well. So these can have 4 to 5 lens elements, so a bit more complicated, a bit more generous field of view. Again, today they are the industry standard, but you'll see some have internal reflections. But they can be had from lesser companies, not like Televue. They're still pretty expensive from Televue, but from your more common telescope manufacturers, they're really inexpensive. Now, the Erfel is the granddaddy of the wide-angle eyepieces. These were invented by Heinrich Erfel in August of 1921, so at least, they're from the 20th century. And they have 5 lens elements, but a whopping 60 to 70 degree field of view. It is a low cost for that wide field, but they do have some astigmatism at the edge. Stars just look a little on the funny side. So now, today, we have the Nagler eyepieces, invented by the late, great Al Nagler and patented in 1979. And these can get pretty complicated. They can have 6 to 8 lens elements, but all Naglers have an 82 degree field of view, which is very generous. People often compare it to looking out the porthole of a spaceship. They do have very few edge aberrations. but they do have a pretty high cost and they can be pretty heavy, which is really important when you're using them with a Dobsonian. With a Schmidt-Cassegrain on a fork mount, no big deal. Schmidt-Cassegrain or refractor on a German mount, no big deal. Just balance it out with the counterweights. But for a Dob, they can throw the Dobsonian off balance. But they are quite awesome. And here's the noted 31 millimeter Nagler, known as either the Holy Hand Grenade because of its appearance or the Terminagler. It's the only eyepiece with a lot of nicknames, but it is cool. Now, more modern is the Ethos. The Ethos was developed principally by Paul Delachae under Al Nagler's guidance in kind of the probably 2000s, maybe into the 2010s. These can have, again, 6 to 8 elements like a Nagler, but they have apparent fields of view of 100 to 110 degrees for the really short focal length versions. The 100 can be available up to a 21 millimeter Ethos, but this eyepiece right here, this thing today, because of inflation, cost over $1,000. So it's $1,000 eyepiece, and we have one in the observatory here in town, and it is awesome. It is great. This is what I call our globular cluster eyepiece. This eyepiece with a 16 inches, it's great on globular clusters, but they are expensive and again pretty heavy because of all the lens elements. So that's a quick crash course in the different types of eyepieces available today. If you're on a budget, get some Plossels, but if you can afford them, get yourself some good Teleview eyepieces. They have much more available too. So I mentioned field of view. So the true field of view that you would have in an eyepiece with a telescope can be approximated from this equation here. So, yep, sorry, more math. So the actual field of view is equal to the apparent field of view, like say 82 degrees, with a Nagler eyepiece divided by the magnification. So, for example, what is the actual field of view of a 31 millimeter Nagler when used with a 22,350 millimeter focal length telescope? This is the focal length of my 9¼ inch f10 Schmidt-Cassegrain. So again, all Naglers have an 82 degree apparent field of view, and 2350 divided by 31 is 76 power. So that gives you a 1.1 degree field of view. That's enough to fit 2 full moons in. So that's a very generous field of view with a long focal length amateur telescope like that. So one thing we'll mention also are diagonals. Usually when you purchase a refractor or Schmidt-Cassegrain, it'll come with one, usually 1¼ inch. Of course, some of the higher end refractors come with 2-inch diagonals. Usually Schmidt-Cassegrains come with 1¼ inch, but I don't believe that's true for some of the Celestron ones anymore. They also come with 2-inch ones. In fact, I remember specifically my 9¼ came with a 2-inch Celestron eyepiece, which I sold because I'm a Teleview guy myself. So there are 2 types out there, 2 basic types. There's mirror diagonals that have a mirror inside, or there are prism diagonals. And it really isn't a huge difference, but mirror diagonals cost less to produce high quality views compared to a prism diagonal. So again, mirror diagonals are more affordable. They do not introduce any color errors to the image like a prism diagonal can, because again, light is passing through a prism, but the colors aren't as split up as with a typical type prism. And the dielectric mirrors do not deteriorate. So the coatings on the mirror diagonal should be good for the lifetime of the diagonal, for a very long time. Now, with prism diagonals, they use a pentaprism or a Amici roof prism, and that may introduce, again, chromatic aberration with short focal length telescopes. So prism diagonals work best for longer focal length telescopes. But again, it's not really a huge difference, and most diagonals that you'll find are mirror diagonals. You'll notice most of these are 90-degree diagonals, like the mirror, the light goes, like in here, reflects at a 90-degree angle. But they're also 45-degree diagonals that, as you can see here from this old one from Orion, I guess I should have updated those, but they're still out there used. This one gives a correct image. So hook up a 45-degree diagonal to your refractor or your Schmidt-Cassegrain or your Maksutov-Cassegrain, and you can use it during the day to look at wildlife, birds and deer and stuff like that, and it'd be a lot of fun. So, you might want to upgrade your diagonal. Now, the one thing I'll also mention is that there are some diagonals that thread on, screw on to the back of a Schmidt-Cassegrain. I don't like those kind because they're harder to rotate. You have to like loosen the attachment here and turn the whole thing. I prefer to use a diagonal like this one for a refractor and use a Schmidt-Cassegrain adapter, because all you have to do is loosen a set screw to turn the whole thing at different angles. But this, like here, for example, this is one meant for specifically a Schmidt-Cassegrain. But again, I'm not a fan of them. I prefer the ones for refractors with a Schmidt adapter. It's like a little tube. There are different types of focusers out there. I won't talk about this too much. I mentioned I have an 8-inch Astrotech Newtonian, and I replaced the Crayford focuser with a one from Moonlight Instruments. And a Crayford focuser means it's gearless. It doesn't have any gears. And I've never been a big fan of those. I've seen some pretty good ones, but they tend to slip a bit too much for my taste. I prefer one like this, a good old rack and pinion focuser. So there's Starlight Instruments. They make the Feather Touch focusers. And boy, they are the best focusers in the world. And they're not too far away in Fort Wayne, Indiana. That's where they're manufactured. One of these days, we should take a field trip there and check them out. So we have a Feather Touch focuser on the back of our Schmidt-Cassegrain. And I've also replaced the focus knob on my 9 1/4 with one of these, because it has a 10-to-1 fine focus as well. Pretty much all the ones, pretty much most focusers today have one. Even the one from Moonlight here is a bit dated, because all of their focusers that they sell now are motorized. So I'm lucky to have one of the non-motorized versions, because I don't really need it for my setup. Now, here are some other accessories we'll take a quick look at. There's the Barlow lens, created by a guy named Peter Barlow, who was an English mathematician and physicist. These are basically have a negative lens that artificially extends the focal length of your telescope. So if you use a 26-millimeter eyepiece with a 2x Barlow, it becomes like a 13-millimeter eyepiece. So you can like double your eyepiece collection with a Barlow. And when I first bought my 10-inch Schmidt-Cassegrain years ago, I really for a while, only had the 26-millimeter that it came with and a Barlow for use with the planets. It was great. But eventually I did upgrade my eyepieces. Now, very similar is a PowerMate from TeleVue, but instead of a negative lens, it uses a positive lens. So if you like look through a Barlow lens, at your feet, it looks like they're far away. But if you use a PowerMate, it looks like your feet are, a bit magnified. So this does a magnifying effect, and it helps get rid of certain aberrations that Barlow lenses create. I won't bother to go into too much detail on that. Also very handy, especially for non-go-to telescopes, are finder scopes. I've always preferred kind of straight through finders, because it makes it you can kind of look above the finder and look through the finder to kind of point your way to certain objects in the sky if your go-tos maybe having a little trouble one night. But some people do prefer ones with right angle diagonals in them. But the one thing you'll have to remember is pretty much all finder scopes show everything upside down. There are corrected versions that don't really degrade the image too much, but again, we tell people to get over it. So pretty much any good telescope will need a finder scope. Most beginner scopes come with small, cheap ones, like a little 5 by 30 or 6 by 30. The minimum you should get is like a 7 by 50 or a 10 by 50 finder scope. Anything smaller just isn't that useful. But some people use one power finders. They don't magnify at all. And these kind of came about through basically those used with guns, like the red dot finder. I'm sure they were made for use with firearms first, and then people realized, hey, we can adapt this to a telescope. So now these little red dot one power finders are very popular. They just project a little dot on this screen here, and you basically, once you get it lined up properly, if you point the dot over a star, the star is going to be in your field of view. A bit more handy is the Telrad finder. These are very popular, and they do these concentric bullseye circles. And last time with binoculars, I talked about the charts from skyspot.com, and those were made specifically for use with a Telrad. And many desktop planetarium programs, like Starry Night or Stellarium, they can be configured to have a Telrad screen projected over the sky, so you can print your own custom star charts. Now, in some cases, a Telrad base doesn't fit on your Dobsonian. Those collapsible Dobs that I showed you from Skywatcher, I shouldn't have bought a Telrad for it because it doesn't really fit anywhere up front. We have to put it toward the bottom of the telescope. What we should have got is a Rigel Quick Finder. It uses a very similar sight, but it's more like a dot with a circle around it instead of the concentric circles. And these can fit in narrower places where Telrads can't. So they're both very good. Telrad or Rigel Quick Finder, it just depends on what type of telescope you have. If you do buy a telescope, one of the first accessories you'll want to get, besides maybe another eyepiece or a Barlow, is a moon filter. Because through big telescopes, like 6 inches and up, especially 10, 12 inches, if you look at the moon with no filter, you'll see it for the next 20 minutes, whether you're looking at it or not. So it'll overwhelm your eyes. So you need a moon filter to cut down on the brightness that your telescope gathers. Now, polarizing filters are more adjustable. They're great for from when the moon, the changing phases of the moon. Maybe you don't want it so dark one night, but you want it dark another night. Or they're great for really bright planets like Venus and Jupiter. They can really dampen down the brilliance from Venus and Jupiter. And there are like minus violet filters too for achromatic refractors. Then there are planetary filters. The different colors show different features on different planets. I won't bother to go in that because it's easier to read that in the companion guide. But I remember back in August of 2003, when Mars was at that historically close opposition, I sold a boatload of number 23A or number 25 red filters because that's a good one for Mars. There are plenty of deep sky filters out there. So your generic deep sky filter, like this one from Lumicon, that's a broadband filter or a light pollution filter. And that's for general purpose for deep sky objects. An UHC filter is an ultra high contrast filter, and that's more specifically for emission nebulae. O3 filters are specifically for planetary nebulae. So like a UHC or especially an O3 filter, those are line filters. Well, a deep sky is a narrow band or a broadband. A UHC is a narrow band, and O3 or H beta filters, those are line band filters. So these specifically let through either light from oxygen 3 sources or hydrogen beta sources. The H beta one isn't really good for too many objects, maybe like the California Nebula or the Horsehead Nebula, but it's not really very useful and so not widely sold. But the other three are, because they can be very, very useful. And of course, if you do want to observe the sun, you can get yourself a solar filter that fits over the front of the objective or the front of the corrector plate. So there's the more Mylar type filters. There's, of course, Mylar. There's Solar Light from Thousand Oaks, or the Batter filters. But glass filters, like those sold with from Spectrum telescopes, they tend to be a little better with contrast. But again, they're glass. They're pretty fragile, so you have to be careful with them. But they are great for observing sunspot groups. So you can just observe the sun on any sunny day with a safe solar filter and check out what's going on our local star. But for a little more action, get yourself a dedicated hydrogen alpha telescope. They used to sell the hydrogen alpha filters individually, especially from a company called Coronado, which was purchased by Meade, then was purchased by Orion, but now all three are gone. But now you can pretty much just get a dedicated hydrogen alpha telescope. Because I did start out with a hydrogen alpha filter that I adapted to my Teleview Prano. But as soon as I sold the Prano, I tried searching for a new adapter to get one made, and it was just a hassle. So I just purchased a dedicated hydrogen alpha telescope. And now, with Coronado gone, Lunt is kind of the king there. They have probably the best hydrogen alpha telescopes out there. Daystar's pretty good, but now Skywatcher is coming out with their own line of hydrogen alpha telescopes. So far, they only have the 100 millimeter style shown here. But this is where all the action is, where you can observe prominences and filaments and just watch them change in a matter of minutes or maybe hours. It is great fun to do. You can still see sunspots, but they're not as good as they are with a dedicated white light solar filter. So it's good to have a little of both. White light filters on normal telescopes for sunspots and hydrogen alpha filters for everything else. It is quite awesome. And there are, from Skywatcher, there's a dedicated solar mount called the Solar Quest. They have this little spotter here that looks for the sun. So those have like a 11-pound capacity. They do have a built-in GPS. They have auto alignment and tracking. There's like a little joystick button on the back. They have, again, all azimuth motorized tracking. They use the Vixen style, the narrower type dovetail plate. And they can be powered by ordinary AA batteries. I purchased the Orion version, which Orion got from Skywatcher. The one I got from Orion didn't work at all, so I sent it back. But I've heard good things about the ones directly from Skywatcher. That they must have gave Orion the junk ones, I guess. Now, of course, if you get a refractor or a Schmidt-Cassegrain, and even to a degree a Newtonian with the secondary, you're going to have to worry about dew unless you live in a dark, dry desert, but not in Michigan. In Michigan, you got to be able to protect yourself from dew. So basically, dew occurs when the actual air temperature falls to the dew point. And, there are nights I've come home where I'm wet and the telescope is covered in water. And of course, I was nowhere near a lake or a pool. It just comes from the air. So with the Schmidt-Cassegrain, even before you buy another eyepiece or a Barlow lens or even a moon filter, you should get yourself a dew cap or build one. You could build one. Even your Telrad should have a dew shield. You can buy that accessory for Telrads or, again, build one. There are many dew controllers out there. Some are very simple, like the one here from AstroZap. Maybe they've updated since then. But Thousand Oaks has one that's also very good. And of course, Kendrick Astro Instruments has really advanced ones that are more temperature sensors and can adjust for the changing temperatures and dew points. So a dew cap will give you maybe a few hours of observing. If you want to observe for longer with no issues with dew, you're going to want to get yourself a dew heater system. These can be wrapped around the corrector plate of a Schmidt-Cassegrain or the objective lens of a refractor or even a finder scope, which is a refractor. Or even with the Newtonians, you can use a secondary heater. You can also get a primary heater because My 8-inch f4 Newtonian primary has dewed up on more than one occasion. But if you do have power nearby, you can get yourself one of these little gadgets or just a regular hair dryer. These are meant to kind of defrost your windshield in your car if it gets frost on the inside. But they can be great for removing dew too. All right. So one more thing to talk about here is electronically assisted astronomy. So this is the use of a technological aid for astronomical viewing. And there are many versions of this. Of course, one's very popular now, but there are light intensifiers like night vision optics. There are video cameras like the ones from Mellencam or the Revolution Imager. And of course, today there's either CCD or really now CMOS cameras because CCDs are pretty much extinct. But above all of those are the smart telescopes. They become very popular in the past 5 or 6 years now. But the purpose of EAA, electronically assisted astronomy, is to view targets in near real time by taking short exposures in a short time period. So you're not actually viewing the objects themselves with your eyes. You're either using a little video eyepiece, which was common with the early smart telescopes, or now predominantly on your phone or your tablets. So they're used to see, more than you might if you were observing through an eyepiece, especially in light polluted conditions. So, again, why use EAA? Because there are going to be a lot of purists, and I'm kind of one of them, because one of the points of observing through a telescope is you are collecting light in some cases that is millions of years old. Light from galaxies traveled for millions of years to come into your eye, but that coolness factor is gone with EAA. You're just looking at a projection or an image on your screen. And you guys know how I feel about the smartphones from part 2 and talking about learning to find the constellations. But under light polluted conditions, they can be very helpful. So, and they can be used to increase the observable details and see dimmer objects. They can overcome vision problems. So if you do have vision issues, EAA is the way to go if you want to be involved in amateur astronomy. And as I mentioned, they are great in light polluted skies. You can view in comfort. You can basically sit down in the field at a chair, or you can even be inside while your telescope is on the outside. It's just that if you think, well, okay, I can be inside in the winter when it's like, 15 degrees out, but nope. The smart telescopes do not work in really low temperatures. So it has to be like in the 30s to roughly 100 degrees or so. But, they're still usable over a wide range of conditions. But if you thought, oh, I can get a smart telescope to, view objects in the winter when it's 0 degrees out, nope, they don't work. So the great thing is, though, a large aperture is not required. And you'll see most smart telescopes are very portable. They're very small. And the equipment requirements are lesser than they are for more dedicated astrophotography. For like astrophotography, you need, like maybe a really good German equatorial mount. But for maybe a smart telescope, they can use a smaller German equatorial mount, but none really do. Or more specifically, an all-azimuth mount. But you can also use a star tracker or some kind of tracking is preferred. And again, pretty much all smart telescopes have go-to. It's kind of a necessity. And pretty much any telescope style, short focal length usually, which are again good for beginners. And most cameras and smart telescopes use CMOS cameras. But again, you can use video cameras on a regular telescope or a DSLR or a mirrorless camera. And it doesn't need to be cooled. So you can do that too if you already have a regular telescope and a video camera, like again a Mellencamp or one of the deep sky imagers, or a regular DSLR camera or a mirrorless camera. So You can view stuff in the near infrared or ultraviolet in EAA. That's something you can't do visually. You can see deep sky objects in color. It is easier to document your viewings because you can save the images. And they are a really cool, different way for sharing astronomy with groups and the public, because you can gather people around your tablet screen or a laptop and show these things to everyone at the same time. But again, the most common way to do EAA today are with smart telescopes. And I know we're going a bit long here, so I'm going to kind of go through this quickly. I won't give you too many details here, but the first types to come along were from Unistellar. So today, though, they have the Equinox 2, which is 114 millimeter in aperture, 114 millimeter Newtonian, with a 450 millimeter focal length at f4 with a 6.2 megapixel sensor. There's also the Odyssey. The standard version has an 85 millimeter aperture, same as the Pro. They both have a 320 millimeter focal length eyepiece. The regular Odyssey has a 3.4 megapixel sensor, while the Pro has a 4.1 megapixel sensor and an electronic eyepiece. But again, that's becoming kind of old-fashioned for smart telescopes. The most common way to use smart telescopes, again, is with your phone or your smartphone or with a tablet computer. So that whole electronic eyepiece is kind of going away. But there is a dedicated eyepiece for regular telescopes today, a smart eyepiece for regular telescopes, but I decided not to mention that here today because they are like $2,000 too. So there's the Pro with the electronic eyepiece. There's also the EV scope for about $4,900. That's also 114 millimeter aperture, 450 millimeter focal length f4, but it has a 7.7 megapixel sensor. Another company called Vaonis has one called the Hestia. It's not really a smart telescope, but you connect your smartphone to it, and your smartphone, when used with the proper app, will guide you to targets. So it's like this lens group to increase the brightness and size of objects when your smartphone camera is used as the imaging sensor. So the telescope itself has a 30 millimeter aperture and magnifies about 25 times. The Vespera now has the Vespera 2 plus a Pro version. They both have a 50 millimeter aperture. The Vespera 2 has a 200 millimeter focal length with an 8.3 megapixel sensor. The Pro has a 12.5 megapixel sensor and a live panorama mode. A bit more expensive is their first one. Oh, there's the Pro, by the way. A bit more expensive is the Stellina, their first model sold. This one sells today for about $4,000. It's 80 millimeters in aperture with a 400 millimeter f5 focal length with a 6.4 megapixel sensor. And if you're extremely wealthy, you can purchase the Hyperia. This is a 6-inch aperture triplet refractor, high-end refracting lenses with a 600 millimeter focal length at f4 and a 45 megapixel full frame sensor. But the cost is $99,000. I kid you not. Boy, you could buy a really advanced setup for that price, but this thing is marketed toward, like museums and planetariums and observatories and stuff like that, where they can write a grant and get one, so most of us can't afford that. But for a fraction of that price, you could afford a pretty advanced imaging system. Now, really new on the scene, they just recently came out, is the Dwarf Lab Mini. This only has a 30 millimeter aperture, 45 millimeter focal length for wide field views, but a 1016 millimeter focal length for the telephoto version. It only weighs 1.9 pounds or 840 grams, and it uses a 2 megapixel Sony sensor. But these were kind of built to compete with the new C-Star 30 that we'll talk about here in a minute. So they're very small and portable. But their most popular one is the Dwarf 3, which just came out not too long ago. This one sells for about $549. The mini sells for about $400, by the way. This one also has a wide field and telephoto version. It uses a 3.4 millimeter aperture for the wide angle, a 35 millimeter lens for the telephoto. It either has a 45 or 737 equivalent focal length. The field of view for the telephoto version is about 3 degrees, while it's up to 45 by 25 degrees with the wide field version for Milky Way views. It has either a 2 megapixel sensor with wide field, or it works out to 8.3 megapixels with the telephoto version. The C-Stars are probably by far the most popular today because of their affordability. And they just recently came out with a more portable version, the S30, but now that's quickly being replaced with the Pro version. They both have a 30 millimeter aperture, 150 millimeter focal length, or at least for the regular C-Star 30. The Pro has a 160 millimeter focal length, but with a quadruplet lens, much more sophisticated lens system. And so the Pro version has a wide angle and a telephoto version, but the regular S30 does not. And then there's that's the Pro version there. I always forget to click for that one. Very popular is the S50. This thing became probably the most common type of smart telescope out there when it was first released. As the name suggests, it has a 50 millimeter aperture with a 250 millimeter focal length and uses a 2.1 megapixel sensor. My guess it'll soon be replaced with a higher resolution sensor. But if you are a member of the Kalamazoo Astronomical Society and do live in the area, we do have one of these for loan, just FYI. Now, if I were to buy one of these things, I would probably get the one from Celestron. So they just came out with the Origin Mark II. This thing uses a advanced imaging system. It's called a Rowe-Ackermann Schmidt-Astrograph. It's a very fast system, f2.2, with a 335 millimeter focal length, but nearly a 6-inch aperture. Same as the Hyperia for a fraction of the cost. These things sell for today about $4,300. The Mark II uses an 8.4 megapixel sensor. And if you did buy one of these with the kind of 6 megapixel camera, you can replace the camera with a newer version. So that's what's really great with this one is you can upgrade the camera. For most of these, if not all of them, you're stuck with the imaging sensor they give you. So those are just some of the smart telescopes available today. There are more. There'll be many more in the years ahead, but probably the C-Stars are the most popular by far. Now, just in closing here are just some observing books that I highly recommend, because sometimes when you observe these things through a telescope, it doesn't mean much unless you can learn about them. So these books are great for, what you can observe and learn more about the science behind them. The ones I really like are the Deep Sky Companions from Stephen James O'Meara, who's like an observing legend. The guy just has exceptional observing skills. He has the Messier objects, the Caldwell objects, Hidden Treasures, and the Secret Deep. And I own copies of every one of those, and I highly recommend them. If you do the Herschel observing program from the Astronomical League, he has the Herschel 400 observing guide, which I own. I honestly haven't looked at that too much. If you really want to learn about the science behind some of these deep sky objects, I highly recommend Annals of the Deep Sky. To date, there are 11 volumes of this thing, and they are packed with information. But for general observing notes, just for observing details about each deep sky object out there, at least many of them, I recommend the Night Sky Observer's Guides. There are like 4 volumes of this now, but like some of those are for the southern hemisphere. So for those of us in the northern hemisphere, I recommend volumes 1 or 2. So finally, the thing I want to leave you with is ultimately none of this matters. What matters isn't the manufacturer, the specifications of the telescope, how advanced the optics are, how good the focuser is, the eyepieces, the mounts, all that sophisticated stuff. The most important thing that you should remember for any telescope, aside from don't buy it at a department store, is the best telescope is the one you use most often. You might be looking through one of these telescopes that you love, and people will say, "Don't you know there's a better version out there?" But if this telescope, no matter how maybe shaky the mount is, if it gets you outside on a clear night, it is the best telescope for you.